maybe you have already learned this is the concept from other courses, but it does not hurt to refresh your memory. The first one I will introduce the string. The string is an engineering string, and this engineering string is defined as the elongation. Elongation L minus L0 is the initial length of your specimen. L is the instantaneous length of your specimen, and divided by this original length of specimen. This is engineering string. So we also have this is a shear string, and look at here. So this is one is the solid one is the original length. So this one is the final length. So L0. So this is shear. And this we just have a shear stress here. So this is angle. Here is angle here. So A, this is the distance of the shear. So the shear string is defined as this gamma equals A and divided by B. So this is the shear string. This is the engineering string. So here is the tensile, compression, and shear, which is the three are commonly seen the cases. And so this string have the concept of the string. Also tensile testing. Maybe are you taking the mechanics solids lab this semester? Okay, if you are taking that lab, and you will do the tensile testing and for different specimens, and for the steel, and for this is aluminum and also cast iron. So what is the tensile test? And we will have this picture, and this figure is called is the engineering stress and strain the figure. So the figure. So here is the strain, and here is the stress. So look at this one. Maybe have you ever seen this is a figure? Is the curve? Okay, if I'm not seen, does not hurt. So okay, so from the origin, and here is a straight line. Straight line means that this is the material, the stress and strain, and they are related proportionally. So this is U. Then this Y is yield point. So after this point, the material will enter the plastic region, and so they will go this way, right? So the highest point is called UTS. It's called ultimate strength. Ultimate strength is the highest strength of this material, and then this specimen will be necking. So look at here. So this is necking. Because of necking here, the stress will go down until this material fractures. So this is how we describe the behavior. This curve. It's called the stress, engineering stress and strain curve. So we have, if we zoom in here in this area, okay, so this is the yield. This is the yield point. The yield point is there is Y. Here is offset. Offset is 0.02%. At this point, if we draw a parallel line and with respect to this is the initial straight line, and we will have this is a parallel line which is dotted line, we will intersect with this curve at this point. This point is called yield point. Okay, yield point means that your material yields. And yields means the plastic deformation occurs. Plastic deformation means that if you remove the load, and the specimen will be covered but not fully, and you will have a residual strain. And that strain is called a plastic strain. Plastic strain cannot be recovered fully. Okay, so these are plastic deformations here. So this is initial uniform elongation, necking, and this is a break. This is a fracture. So this is how we describe this is the engineering stress and strain curve. The several points are very, very important. Yield strength, yield point, ultimate strength, and fracture. So material properties, you can see, whenever we want to describe materials, and we always want to know, and as a mechanical engineer, and we also want to know Young's modulus, yield strength, ultimate strength, is elongation, and it is a Poisson ratio. So these are basic. This is the mechanical properties, and we need to know whenever we want to select some raw materials for our manufacturing processes. So Young's modulus, yield strength, and Poisson ratio are the most important three parameters. So here is the metals, and we have this commonly see this is metals here. So with titanium and tungsten, tungsten is have very high yield strength. But that's the reason tungsten carbide, and also this is used for this is cutting tools in the machine shop, cutting tools. Also, titanium and its alloys are used for this aerospace. So these are non-metallic materials, and so we also have these ceramic and to these spectral fibers. This is commonly seen, and you don't need to memorize this the table. Okay, if there is a need, you can come back and to check the properties of the material you are going to use. So loading and unloading elongation. So this picture, so actually this picture is based upon the engineering stress, engineering strain, the diagram. So this is origin. If we apply the load here, and at this point, and this material enters the plastic region, when plastic deformation occurs. However, at this point, if you remove the load, and your specimen is going to recover, as I said, recover this way, okay? That means this straight line and this straight line, and theoretically, they have the same slope, right? They have the same slope. These two guys are parallel to each other, but when you fully remove your load, and your specimen cannot go back to the origin exactly, and you will have this is called plastic strain. Plastic strain cannot be covered, and only this part, this is elastic strain, can be covered. Okay, so then after you remove the load completely, and then you apply the load again, and you are going to, your specimen is going to begin from this point along these parts, and then come back instead of from this origin again. And when we compare this straight line and this straight line, we know that this is our initial yield strength, right? So this is our new yield strength. Why we have new yield strength? Because from here to here is a plastic deformation, and this plastic deformation just results in the higher yield strength. You understand, guys? This is called strain hardening or work hardening. Question.
So what kind of material is this? Is this like a metal?
Metal, yeah.
Okay.
Basically, this metal, yes. Questions, guys? So I want.
So you said from plastic deformation, you get work hardening. Is it after plastic deformation?
Yes. Yeah. So because here from this is my initial yield strength, right? So if I have plastic deformation, so here this one will be my new yield strength. This new yield strength is usually higher than the initial yield strength. The difference between these two yield strength values is called the strain hardening or work hardening. Okay? So this picture contains a lot of information. What is the plastic deformation? And what is the strain hardening? And why from this is of the strain hardening you will have a much higher yield strength. So I can ask you a lot of questions, and you need to understand and how to describe this one using your own words, right? Okay, great. It's possible. Maybe I will ask a question in our first the midterm. So here, this picture shows the length. This is the elongation, total elongation in a tensile test as a function of original gauge length for various metals, copper, magnesium. This is a lot of other materials. So this one is based on the experiment. So then we talk about the true stress and the true strain. And we know the engineering stress and the engineering strain, right? They talk about the true stress and true strain. I'm going to test your understanding of the difference between true stress and engineering stress and true strain and engineering strain, right? So what is the true stress? This true stress is defined this way. Also, there's the specimen. We have a tensile, also tensile, and we have a tensile load P. So this A here, okay, this A is the instantaneous cross-section area of your specimen. We know that when we pull the specimen, and as it elongates, the cross-sectional area keeps decreasing. Do you agree? Right? Is a decreasing, so this A is decreasing, but this will be my denominator for this equation. On the contrary, for the unusual stress, I have a P, and then the P divided by initial A0. A0 is the initial cross-section area. This is the difference between true stress and the unusual stress. You understand? So regarding the unusual strain, we use this elongation divided by your original length L0. But for the true strain, it's more complicated. It's a logarithmic, natural logarithmic of your instantaneous length divided by your original length. So I want you to be able to tell me clearly how the true stress is different from the unusual stress and how the true strain is different from the unusual strain. Are you clear now? Okay, be very careful. Okay, so this so true stress, we use instantaneous cross-sectional area of your specimen. But for the unusual strain stress, its denominator is the initial cross-sectional area. So for the true strain, we use this equation logarithmic of the ratio of instantaneous length to this is the initial length. Unusual strain is the elongation divided by L0. It's different. Right? So this is, and you can see the true stress, true strain curve, and they never decrease. True stress, true strain curve keeps increasing. Okay, but for the unusual stress strain curve, we have this, right? For this one, keeps increasing. And be very careful. Questions?
I'm sorry, what was the true stress, the one that didn't decrease? And
So this diagram, true stress and the true strain diagram. This curve is keeps increasing. Does not decrease. As long as the true strain, as long as the true strain increases, is the true stress increases. But for the unusual stress and strain, and as if at the very beginning, before it reaches ultimate strength, right? If the strain increases, the stress increases. But after ultimate strength, if your strain is increasing and the stress decreases.
okay, so is it the opposite?
Yeah, so look at this curve. This curve goes all the way up. But for this one, all the way up until this ultimate strength and then goes down. That's the difference between these two diagrams. Question?
Yeah, okay, so on true stress and true strain is basically, it's a log with the initial strain divided by the total strain.
No, L0 is instantaneous strain.
Oh,
L is a instantaneous length. This L0 is initial length. So this A is instantaneous cross-sectional area of your specimen. A0 is the original cross-sectional area. Original cross-sectional usually is the biggest one, right? Before you apply the tensile load. So this so the true stress and true strain, and using abacus, and I'm going to give you abacus modeling homework and to do the metal forming. For the metal forming, you need to specify the true stress and true curve and true strain curve in the software. I'm going to show you. Right? No, not today. I have a video. I'm going to share the video with you. No worries, guys. And then talk about power law flow rule. Power law flow rule. So this is more commonly seen. So this is sigma and epsilon, and they are not a straight line. and but power this flow rule, the power law flow rule. This is a power here. So usually, so these K and N, and they are coefficients, and these coefficients are obtained and experimentally. You need to do a lot of experiments using the same, nominally the same material, and to get this is to do the best fitting, and to get this is the K and N. So then you can just use the K and N to describe the relationship between sigma and the epsilon. Right? So for commonly seen materials and the K and N, they are here. But if we have new materials that means that nobody has done explore this material, and we need to do the experiments by ourselves, and that is called research. Okay, so here you can just use and what other people have done for this commonly seen these materials. So this is for different materials, and we have different true stress and strain curve. As you can see, the different materials, copper, steel, brass, and stainless steel, and different steels, and they are different also. I just show you this one. If there's a need, yeah, you can come back to look at these slides to get what curve you want. So idealize the stress strain curve. So this is well, this one is a perfectly elastic. That means we just assume, but this does not exist at all. Okay. So here is the perfect elastic. It does not use at all, and you always go from origin, apply load, then really remove the load, and come back to the origin. So this is a perfect elastic. So this is rigid. See, B is a rigid, and perfect is plastic. Rigid means that whenever, however you strain, and it yields, so it will not. This is sigma. The stress does not change. So C is elastic. At the very beginning, elastic, and then perfect plastic. And perfect plastic means that, and there is no strain hardening. Right? I just introduced the strain hardening. Strain hardening means that if I have some plastic deformation, and I can increase the yield strength. But here, perfect plastic means that no matter how much plastic deformation and you have, and you will not increase the yield strength. See, I have plastic deformation here, but my yield strength does not change. It remains the same. Right? This is called perfect plastic. So here is a rigid. So D is a rigid linearly strain hardened. So this is rigid at the very beginning. Rigid here is linearly hardened. This is hardened. Hardening means that if there is a plastic deformation, the yield strength is increased. So this is hardening. So here is a elastic linearly hardening. So this one is the most commonly seen materials. Elastic and then the linearly hardening. So this is several cases here. The effect of strain hardening exponent on the shape of these true stress strain curves. So this exponent plays a very, very important role. So this is you can have different shapes. The temperature and the strain rate effects. And we know that the temperature has a very, very important role for this stress. You can see as the temperature increases, so elastic unit modulus and the tensile strength, and they are decreasing. But ductility, yield strength decreasing also. However, elongation is an indicator of ductility. The ductility increases. So yes, the strength and ductility, and they are kind of competing the properties. If one is high, another one will be low. You cannot have a material that have both high strength and high ductility. You understand that? Usually, if this material is very, very strong, it's very, very brittle. Ductility goes down. However, if ductility is very, very high, is weak. It will not be strong. Right? So this is are competing. Ductility and the strength, and they are competing. So here is the strain rate, and the strain rate. This is the tensile strength. A strain rate and has a dominant, has a very the obvious effect on this is the tensile strength also. So if you have has a chance of operating some machines, manufacturing machines, lathes, milling machine. So all these metal cutting that involves the very high strain rate, right? A high strain rate, and we need to use if we want to model them, and we need to use Johnson-Cook model, and to accommodate this is the effect of strain rate. There are typical strain rates in metal working. We have cold working and hot working is a machining. I'm a machining guy. Machining means the metal cutting, material removal processes, lathes, milling, and so these kind of things. And cold work, and this is hot work. So what's the difference between cold work and hot work? I want you to draw down, okay? What's the difference between cold working and hot working? The difference is that for cold working, the operating temperature is below the recrystallization temperature of this material. Hot working means that the temperature, the operating temperature is above the recrystallization temperature of this material. Recrystallization. So that's a very important temperature for all these metals, especially for metals. Cold working and hot working, the difference. I might ask you, and please use your own words, tell me the difference between these two processes. So machining is more complicated because there is a separation of the cakes from the workpiece. So this definitely includes the friction, involves high temperature and the large deformation. The sheet metal forming and the superplastic forming. So this is a large deformation involved also. So based on this slide, I want you to know what's the difference between cold working and hot working. The difference is the recrystallization temperature.
What was the definition of cold working again?
Recrystallization temperature?
Yes.
Cold work. Cold working, you mean? Yeah, cold working means that the operating temperature, the temperature at which you operate this process, is below the recrystallization temperature of your material, of this material. Different material has different recrystallization temperature. The hot working means that the operating temperature at which you are operating the machine is above the recrystallization temperature. Usually hot, you need to elevate the temperature. Cold working usually we just do it at the room temperature, right? So for this one, they have different deformation speed and strain rate. This just give you a range. As you can see for machining, machining the strain rate is so high, very high, 10 power 3 to minus to 10 power 6. And then we talk about the homologous temperature. So there is one definition you need to know what is a homologous. So when I was a student, whenever I learn something new, I pay more attention to it. It's a homologous. Have you guys ever heard this temperature? No, right? If no, you can just write down. Okay, so homologous temperature means it's this one. Okay, so dT is your operating temperature, the testing temperature. M is your melting temperature of the metal. So the ratio of these two guys is called the homologous temperature. So homologous temperature, see, this is the curve of the effect of homologous temperature. See, so this is the strain rate sensitivity exponent M. So the homologous temperature has a strong effect on the strain rate sensitivity exponent M. If this ratio is very high, see, this M is increasing exponentially. Okay, so what I based on this slide, I want you to know how we define the homologous temperature, and it is equals the ratio of operating temperature or testing temperature and to the melting temperature. The strain rate effects, and strain rate, this is the strain rate effect, and C is a strength coefficient M and all C and M, and they are obtained experimentally. So this epsilon dot is the strain rate and sigma here. So here is the for commonly used material at different temperatures, and we have different C and M. The C have two values for each of these material. One is for the PSI, one is for megapascal. It depends on what kind of unit you are using. If we use English unit, you need to use this column. If you are using international unit, you need to use this column. Right? Pay attention to this which unit you are using. But I'm just a ratio. It doesn't matter on what kind of unit you are using. Questions? I don't expect you to remember everything. I just have some idea on what is the strain rate effect looks like. Just like then come back and to get this equation and then find out on what kind of values you should use. And this depends on what material you are using. Okay, so this effect of strain rate sensitivity on elongation. So this is M. So this is M here. So this is the total elongation. This is the strain rate. Exponent M on the total elongation for various metals. So there's different materials, and we have different curves, different materials. So see. So this is a post uniform elongation. Then the hydrostatic pressure. What is the hydrostatic? What is the hydrostatic? Hydrostatic pressure means that the pressure is at the same value from different reactions, right? Just like as in the water, right? Okay, this is a hydrostatic pressure. If for this is the Q, for this is element, if we have the same magnitude of pressure from different reactions, so this is a hydrostatic pressure. So here, the hydrostatic pressure, effect of hydrostatic pressure on the true strain as a fracture. So the true strain as a fracture. This is yes. This one is very vertical line. So this is very beautiful curve. This is kind of kinky. So here is a very beautiful curve. Right? So here's a beryllium. That's a beryllium. Beryllium in the compressing around the solid cylindrical specimen. Beryllium just look like a barrel. Why? What is the reason for this beryllium? Because of friction. Because of friction as a bi-specimen interface. So, so this one maybe you need to know this one. Okay? Why we have this beryllium phenomena? The reason is that there's a friction between the die and the workpiece. We will do metal forming modeling using Abacus. I'm going to give you the video and the detail of the video, and then you can do it by yourself. Plane strain compression testing. The plane strain. So do you have idea what is called a plane strain? What is a plane stress? Okay, if you do not know plane strain, we say is a thick, kind of thick plate. Thick plate. Plane stress is a thin plate. Right? Plane strain. This is a plane strain. We can see this plate is kind of it's a decently thick compression test. So this is yield strength in plane strain. So y prime equals this. This is y is a bulky. Is a bulky, the yield strength of the bulky material. The size matters. It's a little bit high than the bulky, the yield strength of the bulky, same material, bulky material of the same material. So tension and compression, this is tension and compression. The two stress and the two strain curve in tension and compression for aluminum. And for simplicity, we just treated them identical, right? Compression and this tensile as identical. So this Bolsinger effect, I want to introduce the Bolsinger effect. Maybe you need to know how to describe this effect using your own language. The Bolsinger effect means that for this case, okay, so this is my load, this is the tension. If I apply load, it goes this way. If I remove a load, it will not go along this original path. It will go another path. This is called Bolsinger effect. Bolsinger effect is a very, very common phenomena, not just in mechanics, but also in the sensor. In the sensor, we also have these kind of things, input and output. Loading, we call loading, increasing the input, we have output, and then decrease the input, the output will go another part. It's called Bolsinger effect. Bolsinger effect will accompany the loss of energy, right?
So is it a result of either doing compression and tension, or vice versa? It becomes weaker in its
The Bolsinger will become bigger. This is yield strength. It will become bigger.
Oh, okay.
It will become bigger, but from there, and they will have energy loss. But it will become the yield strength becomes bigger. This is a new yield strength.
Okay.
Question? Here is the two test disk. This is a disk. We have a load here, and you can see it fractures in the middle. So this is sigma equals 2p divided by pi dt. T is the thickness of this disk. The torsion testing. The torsion. If you are you taking mechanical solids lab now this semester? You will do the torsion test. Torsion test, you have several specimen and apply the load on this specimen torque, and then you keep rotating, keep applying load, and finally it fractures, and you will see. And that's called torsion testing. Torsion testing, we have tau. Tau is a torque. So this is R, and so this is the T here. Right? So this is gamma here. So this the phi. This is R phi. So here is R, the length. But our torsional test is kind of different from here because our torsional test specimen is uniformly throughout. This is longitudinally the uniform. But here they have a notch here. So 3 and 4-point bending test is a 3-point bending test and 4-point bending test. And how to calculate? And we use this equation, sigma equals mci. I is the area moment of inertia of your specimen. And C, what's the C, guys? And C is the distance between the point of interest and to the neutral axis. You know neutral axis, right? Neutral axis. Okay, here. So this one, because it will bend, right? It will bend So here in the middle, here is a neutral axis. Neutral axis means that if we put fibers from left end to right end, and fibers, layer by layer fibers, if I press it, right, I know that on the top, the fibers will be elongated, and in the bottom, the fibers will be compressed. So in the middle, there must be some fibers that their length does not change. So that is called the neutral axis. Okay? Neutral axis means that on this plane, on this axis, if I put a fiber, this fiber's length will not change before you apply load and after you apply load. This is called neutral axis. The C is the distance between the point of interest and to the neutral axis of your specimen. Okay, so this is my specimen, right? This is my specimen. So this is my specimen. Now I bend it, right? I bend it. I know on this side, some layers of the fiber are going to be elongated, right? See, because I bend this way. But in the inside, so I know because I bend it this way, the fibers, if I put the fibers here, these fibers will be contract somehow. Contracting and elongating, but in the middle, there must be a layer on which the fibers do not contract, do not elongate. That means the length of the fibers on that layer is remain the same. That layer is called neutral axis. Right? So hardness testing. Hardness testing, we have Brinell, Vickers, and Knoop, and Rockwell. And the Brinell and Rockwell are commonly used one. So if you take the mechanical engineering lab and you will do the Rockwell testing, actually, to be exact, you will do the C and C skill. So that's the reason on your hardness, the hardness you get will be HRC. H stands for hardness, R means the Rockwell, C means the C skill. Okay? Because when I taught this Army lab, the hardness testing machine I used is HRC. But Brinell is another system. And the Vickers and Knoop, and they are the Brinell and the Rockwell are commonly used one, but people also use Vickers and Knoop. You should know, it's a hardness testing. Are you taking Army lab this semester? No. Okay. So hardness testing consideration. So you can see. So in addition geometry, for the Brinell hardness testing, this is a spherical ball, annealed metal, this annealed metal, this is a work hardened metal. So notice the difference in metal flow as a periphery of the impression. So this is a periphery of the impression. So here is a bulk deformation in mild steel under a spherical indenter. This is have a spherical indenter, and then you just cut it, right? And using some machine to cut it, you will see it looks this way. So here relation between the Brinell hardness and yield strength for aluminum and steel. So people have found the relationship between Brinell hardness and yield strength. And you need to be very, very careful. And this relationship is only for Brinell hardness, not for Rockwell hardness. You understand? And what I meant is that for this material, if you have HRC, which is Rockwell hardness, and you cannot use this relationship, what you need to do, you need to convert HRC and to HB. HB is Brinell hardness. and then use this one to get the ultimate strength. You understand? So remember, keep in mind, and this picture is only for the Brinell harness and the yield strength, not for the hardware, not for the Rockwell harness. If you have the Rockwell harness, and you must convert the Rockwell harness into Brinell harness, and then use this figure and to do some calculation. Otherwise, and your answer will be totally very weird, very confusing. The fatigue, fatigue means that you apply load, the cycle apply the cycle load. So this is for the ferrous, this is the metal. For this steel, we have endurance limit. So you can see endurance limit is a horizontal line. For this is non-ferrous, this is steel, non-ferrous metal, aluminum, and we don't have this clear cut. This is a knee, just like the knee, right? A human knee. So this we don't have this endurance limit, and you should know that. So this is called SN diagram. N stands for the number of cycles. S stands for the stress. So remember, for this is in the CAE class. If you take a CAE class with me, and in these four, so we will talk about endurance limit. And for the ferrous, the metals, and ferrous metals means that this metal contains iron. Okay, for ferrous metals, we have a very beautiful this curve. So this is endurance limit. Endurance limit means that if your stress, if you don't apply the stress, is lower than your endurance limit, theoretically, right? No matter how you apply this load, and your specimen will not fail. But this I just say theoretically. Practically, there is a lot of defects in the specimen. It's not true for the practical. Be very careful. So this is called SN diagram. For these other steels, other metals, we don't have this beautiful picture. Question?
What did you say the definition of endurance limit was again?
So endurance limit means that if the load you applied, okay, is lower than this endurance limit, then theoretically the fatigue life of your specimen is infinite. No matter how you apply it, theoretically your material will not fail. But this is theoretically. Practically, it's not true because there are a lot of defects in the material. Okay, this is crepe. Almost time there. So this is tensile strength. This is the endurance limit. So crepe is a crepe have the same very beautiful the curve, 3 stages: primary, secondary, and tertiary. The crepe impact, and you will do the annual impact, and this is the copy impact and in the ME lab to see and what is the toughness, how much energy this specimen can absorb before. Residual stress here and the distortion. Residual stress is very important. Usually